Okay, hi, my name is Caitlin Grasso. I am a PhD student at the University of Vermont in computer science, and I'm also part of the Proteus Institute, and this is ProteusTV. And ProteusTV will be streamed here every other Friday right now from 3 to 4 p.m. And you can come on here and learn about AI, robots, and biology, and much more. And today I'm going to be coding up a cellular automaton for you all called the Game of Life. And that's what you see playing in the corner of my screen right now, the bottom corner. So first I'll just talk a little bit about what cellular automata are, and specifically what the Game of Life is, and then I'll get into some coding. So cellular automata are mathematical systems that consist of a grid of, or a lattice of cells, and each cell in that grid holds a specific state. And these states are repeatedly updated based on the state of that cell and the state of just its neighboring cells. So the grid is updated based on a set of local rules for each cell. And several processes in biology, chemistry, and physics that depend on just local interactions can be simulated using cellular automata. And then the behavior of these cellular automata can be observed to learn something about the system that it's simulating. So the Game of Life in particular is a very famous cellular automaton that was invented by John Conway in 1970. And he initially set out to create an interesting and unpredictable cellular automata. And he also drew inspiration from biology to create a simple set of 4 rules that produced some pretty interesting behavior. So in his CA, there's only 2 states. Cells in the grid can either be alive or dead, and there's 4 rules. And these 4 rules are, as I said, kind of draw inspiration from biology and consist of a death rule, or 2 death rules. So cells in this grid will die off if they have too few neighbors. So if they're too isolated, they will also die if they have too many neighbors, so they're overcrowded. And then the other 2 rules are that cells that are alive that have just the right amount of neighbors will stay alive, and a cell that's dead will turn on or become alive at the next time step if it has also the right amount of neighbors, a healthy amount of neighbors. So since he created these rules in 1970, it has become very popular, mostly because of the surprising and interesting behavior that it can produce just from these simple rules. So from a randomly initialized grid of cells, so a random grid of cells where some are alive and some are dead, and with just these simple update rules, some patterns emerge, and we can observe self-organization. So if you see the video in the bottom right corner, you'll see when it starts over that it appears to be completely random, and then it appears that something organized is happening. Even though we know that nothing is coordinated on a global scale, it looks as if something coordinated is happening. So the cells in this grid can only see themselves and the neighbors around them, and then they update themselves based on that, and it's interesting to see the behavior that results. So this is what I will be coding up today, and I will be using just Python and NumPy and Matplotlib. So NumPy and Matplotlib are Python libraries, so if you'd like to follow along, feel free. So I will start just by importing those packages. And then we're also going to use Matplotlib's animation package. Oops. Okay. So as I said, CAs consist of a grid of cells. So first we need to define our grid of cells. So I'm just going to define a variable called grid size, and for now we'll make this very small. So we'll just say this will be 3. So right now it's just going to be a 3 by 3 grid of live and dead cells. So now we're going to go ahead and create our grid. And to create our grid, as I said, it's going to be randomly initialized 1s and 0s. So we're going to use NumPy's random.randint function, which takes a low. So our low is going to be 0, which is going to be our dead cells. So this is the white in that grid, is the empty space or the dead cells. And then our high, we want it to be either 0s or 1s. And because this function excludes the high value, our high is going to be 2. And then the size of this array will be the grid size by grid size. Okay, so now we can just print out our grid to make sure that it is an array of 1s and 0s. So it's 3 by 3. And we have an array of 1s and 0s, and it's 3 by 3. So I'm also going to just set a random seed, the random number generator, so that we get the same array while we are debugging. So this will be the array that we're working with while we create the game of life. Okay. So now we have our initial grid of cells. So the next thing to do is update this grid so we can see what state each of the cells are in at the next time step. So to do this, we need to iterate through time. So we'll create a for loop. And right now we'll just go through 2 time steps. And we'll print out t. So okay, so at t equals 0, this is actually our grid. So we're going to start at t equals 1. Okay, so at time equals 0, this is what our grid looks like. So this is the initial condition, our initial configuration of 1s and 0s. And then at the next time step, we want to figure out what each of these cells, what state they will hold, and see what the grid looks like at the next time step. So now we need to update each of these cells in a row. And so to do this, what we need is the number of neighbors that each cell has. So in a cellular automata, because it depends on just local rules, we need to know the neighborhood that we're working with. So as we iterate through the cells in the grid, we need to know how many of their neighbors they are able to see. And traditionally in the game of life, if we're focusing, for example, just on this center cell, it can see all 8 of its neighbors. So top, bottom, left, right, and then the 4 corners. And so this is called a Moore neighborhood when you can see all 8, versus another common neighborhood, which is von Neumann, which is just the top and bottom and the left and right. So we'll use a Moore neighborhood. And so we need to figure out how many neighbors are on, so how many live neighbors each of the cells have. And so to do this, we can use something called a kernel, and this kernel is going to have the same dimensions as the neighborhood. So as I said, if we're focusing, for example, on the center cell right here, and we would like to know how many neighbors the center cell has, we're looking in this 3 by 3 neighborhood. So the kernel is going to be a 3 by 3 array, and it's going to consist of 1s in every spot where there's a neighbor, and a 0 in the spot where it's the cell itself that we're focused on. And what we can do with this kernel is multiply the kernel by just the subset of the array when we're centered on the cell we'd like the number of neighbors for. And that will give us back the ones where there are neighbors and a 0 right in the center. And then we can sum up that array to figure out how many ones there are in this neighbor region. So I'll first create the kernel. So it is going to be an array of ones. That's the size of the neighborhood, which again, it's a 3 by 3 neighborhood. So this is an array of ones, but we also want a 0 in the center of this array so that it cancels out the cell we're focused on. So we never add in that as one of the neighbors when we're counting up how many neighbors there are. So you don't want to include the cell. And then we can, so to do that, we want the kernel at 1, 1 to be 0. So now we can print out our kernel. And we also want it to be integers. Okay, so this is our kernel here, and as I said, it's ones in all the positions where there's a neighbor, and a 0 for the cell itself that we're trying to get the number of neighbors for. So if this is our world and we'd like the number of neighbors for this cell in the middle, we can go ahead and multiply these two arrays, and it'll cancel out the center cell and give back just an array of the neighbors, of ones where the neighbors are. So if we go ahead and do that, and I'll put some lines in between here so it's easier to read. Okay, so now we'll just multiply the grid and the kernel, and we should see that it looks the same as this array but canceling out this center cell. And that's exactly what we get back. So now, again, this position, or this cell here, is the cell that we're trying to find the number of neighbors for. And now we have ones in the positions where there's neighbors of that cell, so we can just go ahead and sum up this array, and that should give us back the number of neighbors that this cell has. So if we wrap this in just the sum function, we see that it tells us that the center cell has 6 neighbors, and if we go ahead and count those, so we're focusing on this cell here, there's 1, 2, 3, 4, 5, 6 neighbors in the cell's neighborhood. So that's how we can get the number of neighbors. And again, the reason we want the number of neighbors for the cell is to figure out what state that cell will become in the next time step. So that's based on Conway's game of life rules, where if there's too many neighbors, the cell can die. If it's isolated, it can die. And if it's happy, it'll stay as is or be born. Okay, so I will go ahead and delete this. So now we just found out how to get the number of neighbors for the center cell, but we have to do that for each cell in the array. And so we're going to iterate through each of these cells, starting with this cell here. And the problem with this right now, though, is that we can't overlay our kernel. So remember, the kernel has to be overlaid where the center of it is on top of the cell that we're trying to get the number of neighbors for. So this 0 here would have to line up with this 0. And because this cell has no neighbors, it's on the edge, it has no neighbors to the left or on top, we need to alter this so that we're able to overlay this array on top of this array when it's centered around the corner cell here. So to do that, we need to add a layer of zeros around this array. So I'm going to define a temporary array called temp, and it's going to be our grid, but with an extra layer of zeros around it. So we can use NumPy's pad function, and it takes the array we're trying to pad, which is grid, and then the pad width is going to be 1, so we only want one extra layer of zeros around the array. And by default, this will pad it with 1s. So now if we print out our temporary array, temp, we should see the same array here, but with a layer of 1s around, or a layer of zeros around it. And so that's exactly what we see. There's zeros, and then the center array, the center 3x3 array is exactly what our grid is. Okay, so now remember our first cell that we're trying to get the number of neighbors for is this corner cell. And now there's enough space to overlay the kernel on top of it. So we can index this temporary array to find just this subarray, this sub 3x3 array, which is centered around our corner cell, so we can multiply the kernel on top of it. And so first we need the index of this cell here, and we're going to iterate through each of these cells and find the index, and then find these subarrays so we can find the number of neighbors. So we will first iterate through the rows and columns of this array. So for R in range, so we only want to find the number of neighbors, or we only want to update the inner cells of this temporary array. So we want to start at this cell and end at this cell. So when we're iterating through the rows, we're actually going to start one row in. So we're going to start at row 1, and then we're going to also end one row early. So it's going to go from 1 to the shape of, so this is the number of rows of the temp array, so this many rows, and then we want to end one early, so we're going to do -1. And then it'll be the same thing for the columns. We're going to start one column in, and we're also going to end one column early, so it'll be from 1 to the number of columns, -1. So now the cell is going to be the temporary array at row R, column C. So at first, R will be 1, C will be 1, that's this cell here, and it's stored in the variable cell. And so now we need to index temp again to find this 3x3 neighborhood of the cell. So we'll call that the neighborhood, and it'll be temp. We want to start at, so the position here is RC, so we want to start at row -1, so we want to start one above and end at row +1. And same with columns, we're going to start one column to the left and end one column to the right. So that's these two cells is where we are indexing this array. So we're going to start at row, which right now is 1 -1, so that'll be 0, row 0. And we want to go to row +1, so we want to go from 1 to 2. But because it's exclusive of this end, we're actually going to add 2 instead of 1. So that'll tell us to stop at the row +1. And we're going to do the same thing for the columns. It'll be column -1, the column we're on -1, and then the column we're on +2. So if we print out our neighborhood now, we should see that it's just this 3x3 sub-array of our temporary padded array. Oops. Oh. And we will just stop there for now, not keep iterating. Okay. And we have this 3x3 array, which is exactly the same as the first 3x3 chunk of this larger array. Okay, so again, we're focused on getting the number of neighbors of this center cell here, which is the cell here, and which is also, again, the corner cell or the first cell of our original grid. So now we can overlay, we have a 3x3 matrix, so we can overlay our kernel right on top of it, which will cancel out this center cell, which is already 0, so it won't be doing anything, and multiply on top of each other to get the number of neighbors. So we'll call it the sum of neighbors. So first we're multiplying the kernel with the neighborhood. So this will give us back the array with the center cell canceled out. And then again, we're going to wrap that in a sum function, so we're actually summing up how many neighbors there are. And so this should give us back 2 in our case. Still looking at this array. And it does. So this is the number of neighbors that our first cell in our original grid right here has, and it does have 2. So now they don't print the temp or the neighborhood, and I just print the sum of neighbors. We can check to verify that it's correctly telling us how many neighbors each of the cells has. So the first cell here has 2 neighbors. The second cell, which is right here, should have 3 neighbors, 1, 2, 3, which it does. The third cell has 3 neighbors. The fourth cell has 1, 2, 3, 4, which it does. The middle cell has 6 neighbors, 1, 2, 3, 4, 5, 6. So we can see that it's correctly giving us back the number of neighbors, and so on. So now that we have that, we can go ahead and apply the rules to each of these cells to figure out what state it will become in the next time step. So as I said, there are four rules. And we'll start with the first 2 of those rules, which tell us when live cells will die. So the first rule is if a cell has too few neighbors, it will die of isolation. And Conway defined too few neighbors as being less than 2 specifically. So the first criteria, though, that we have to check is whether or not that cell is alive or not. So a cell can only die if it's already on. So first we have to check if the cell is equal to 1. So remember, live cells in our grid are 1, dead cells or empty space is 0. And if that cell has less than 2 neighbors. So we know that the number of neighbors that cell has is stored in sum of neighbors. So we'll go ahead and check if this is less than 2. And this is our isolation rule. So if it does have less than 2 neighbors, then that cell at the next time period will become 0. So what we want to update now is the grid. So this is our original grid of cells. And so what we're going to be updating is the grid at row column. The row and the column we're on is going to be equal to 0. But because our row and column are dependent on this this temporary array, which is actually larger than our normal grid, it's a 5x5 array because we added that extra padding instead of a 3x3 array. These are actually 1 indice off. So we actually will be subtracting 1 and this 1. So here, when our for the first cell, our row and column will start at 1, 1. In the actual grid, that's actually at index 0, 0, because we don't have that padded layer anymore. So now we're changing the grid at the first cell to be 0 if it has too few neighbors and if it's already on. And the reason we don't change the temporary array is because we're doing an asynchronous update. A synchronous update. So all of the cells in the grid are updated at once, so basically we are getting our information for how many neighbors each cell has from the original grid before any updates in the current iteration are happening. So that grid stays the same, and each cell is updated based on the original state of that grid, not based on anything that changes inside updating each cell in the same iteration. So we're updating this grid. And then our next rule here is going to be also a death rule, but instead of isolation, cells can die if they have too many neighbors or they're overcrowded. So again, we'll check to see if the cell is on or alive, and then we will see if the sum of the neighbors has greater than 3 cells. And Conway defined greater than 3 cells as being overcrowded. So if that's the case, then that cell will become 0 at the next time step. This is overcrowded. Okay, so our next rule is going to be the stasis rule. So if a cell is alive and it has just the right number of neighbors, then it'll stay alive. So we saw that if it has less than 2 or greater than 3, it will die. So if it has equal or exactly 2 or 3 neighbors, it will continue living. So then the grid, so then it will stay alive. And we don't need this in here because if we did nothing, it would also stay alive, but for clarity, we'll put it in. So this is the stasis rule. And then our last rule is the birth rule. So if a cell is dead and it has exactly 3 neighbors, then that is enough for it to become alive in the next time step. And this is birth. Okay. So this concludes a single update of our grid. So if we go ahead and print out our grid here, we should see it appropriately updated based on these rules. Okay, so we see that the first cell was dead and it only had 2 neighbors, so it stayed off. The second cell had 3 neighbors, which is falls under our stasis rule, so it stays on. Same with the third cell. And then the middle cell here had 6 neighbors, so it turned off because of our overcrowding rule. 6 is greater than 3. Same with this cell, it had 5 neighbors. This cell had 2 and it was on, so it stays on. This cell had also too many neighbors, and then lastly, this cell had 3 neighbors, which is a good amount of neighbors, so it stays on. So we see a successful first update. We can go ahead and expand this. to another time step to see it update again. I didn't save it. Okay, so we see that almost all of our cells died out except this one. So in our last time step, they all had too few neighbors, so they all died, except for this one here, which was dead, and it has exactly 3 neighbors, so it became alive. So now we have 1 here. And then if we continue for 1 more iteration, I'm sure you can guess what will happen. And all of our cells die out. And once they're all died out, none of them can turn on again, because in order to turn on, you need exactly three neighbors. So for a grid of this small, it's not a very interesting game to play. But we can increase the size of the grid and visualize the dynamics that will take place. So in order to better visualize this, we're going to use NumPy or Matplotlib's animation package. And so the first thing that we're going to start off doing is by plotting the initial condition, or the initial grid. And we'll also go ahead and increase this grid size to 50, so it's a little more interesting. So we're going to use Matplotlib to plot the initial grid. And specifically, we'll use the matShow because it's a matrix function. And we'll set the color map to binary. So there will be a 1, or it'll be black where there are 1s and 0, and white where there are 0s. Okay, so if we just show this, and I'm going to comment out all of our updating for now. So this should just show us our initial condition. So here we just have a randomly defined matrix of 1s and 0s. And this is our initial grid. And I'm also just going to turn off the axis here so it looks a little nicer. So this is our initial grid. Okay, so the next thing we're going to do is iteratively update this figure so that it shows the next states of our grid. And to do this, we can use Matplotlib's animation function. And the syntax for what that looks like is like this. So the actual function is called funcAnimation. And what this function takes is a figure to be updated. So in our case, that's going to be fig, because we defined it up here, and also a function that we're using to update this figure. So the figure we're updating is called fig, and that holds the grid that is being plotted to this figure. And then the second thing we need is a function. And so right now, this is going to be our update function. So funcAnimation has a loop for us, and it'll iteratively call the update function and plot it in the figure. So what our update function is actually going to be is just this inside here of the loop. So we actually don't even need this loop now because the funcAnimation function runs the loop for us. So we're actually going to make this into a function called updateGrid. And what this function has to take is a frame. And the frame is just the time step, or the frame that we're on in the function, in the update. So we can get rid of that. And also this function needs to access the grid. Okay, and then the last thing that we need to do is actually change the data that's being showed to the figure in this function. So we're going to use the setData function, And now, again, we're going to show the grid, but because the grid has just been updated after this function has been run, it'll show the next state of the grid. So now we should be able to play this, and it'll show our cellular automata updating over time. Okay, and I used the wrong, so instead of ax.setData, okay, so I need to store this in a variable, and then it's going to actually be mat.setData. So this is our matrix that's being plotted to our figure, and we are setting the data of that matrix to the grid every time. And here we go. So here's the game of life on a 50 by 50 grid. And we can see some of those interesting patterns start to emerge. So we see some static configuration. So these cells, for example, are happy not moving because they have the perfect number of neighbors. And then we see some oscillating patterns. So these lines, for example, are oscillating between two states. And then there are just other interesting patterns that can emerge in this game. We see some interesting ones over here. Some patterns will look like they're actually moving across the screen. There's a famous one called a glider that does this. And it's interesting because the only thing these cells have access to is just their local neighborhood. But we still start to see some interesting patterns observed. So we can go ahead and even increase the size of the grid even further and make it 100. And we can try to go even higher than that, move it 500. Which might take a lot longer. Yep, so this is super high. But it would be interesting to let this play out a little bit and see what happens. Yeah, but it takes a little time to run, so I'll go ahead and change it back to 100. But it's interesting to see how carefully Conway defined these rules. So they're very sensitive to even the smallest changes. So for example, if we say that a cell will be born if it has 2 or 3 neighbors, so we change it to not just 3, but if it has 2, it can also be born. We can look at what effect this has. And we see far less interesting structures emerge. None of those oscillating patterns or static patterns or even anything interesting really. We see a lot more live cells, and obviously that's because more cells are being born. But as you can see, it's far less interesting than the actual game of life. Oops. We can try to change another rule. So so we can change this to just just 2. So now a cell will only continue to survive if it has exactly 2 neighbors. And so we can change this to greater than or equal to 3. So if it has 3 or more, then it's too crowded, it will die. So what you might expect here is that more cells are dying. and you can see that they die off much faster, and we're just left with these oscillating or static structures. So there's a lot less going on here, and what Conway was hoping was something for a CA where patterns never die off, sometimes die off, something a little more interesting. So that small change also really changes the dynamics of the game of life. So this should be the actual game of life. And people have made really cool variations to this game by making it continuous or just doing it on really large grids, and also carefully selecting the initial conditions of the grid so that it produces specific behaviors. So there's a lot of really cool stuff out there that's easy to find, that's really interesting on the game of life. So like this is an interesting pattern here. But this is all I have. So be sure to tune in on Fridays at 3 to 4 p.m. for more interesting content on coding, on robots and AI and biology and more. But yeah, thanks for listening. Bye.